Okay, so here we're in section 7.7. I know I skipped some. We're talking about hydrostatic pressures and forces. Okay, pressure, or hydrostatic pressure, is basically a force or a weight, if you want, density of a fluid and force density, for instance, would be things like pounds per cubic foot or newtons per cubic meter multiplied by the depth. Of the fluid. Okay, and you have actually seen a couple of have had some real world experiences with hydrostatic pressure. First example I'm going to talk about is basically atmospheric pressure, because this works for a lot of gases too. Now, the important thing about hydrostatic pressure is it's equal in all directions. In other words, the pressure is independent of your orientation. Only depth. Okay. So with hydrostatic pressure, you should notice that remember that it decreases with increasing height above sea level. And the reason for that is that the amount of air above you decreases as you go higher. All right, the second example then is diving in the swimming pool. And I'm sure you've all swum in a swimming pool. All right, so if we've got a swimming pool, and this is the depth of water. All right, so and this is the top of the water. If you're down here, your ears are going to feel less pressure than if you're down here, and the reason is because you've got less water on top of you here than you do here. All right, and again, the pressure it exerts is the same in all directions. I have seen where they have sent a styrofoam head, like you see with a lot of wig things, down on a bathyscaphe, some of these deep submersible submarines, into a deep trench. And when it came back up, what used to be about 1.5 to 2 feet has now been shrunk down to something which is about 1 inch high. It started out around 2 feet high, and it ended up being about 1 inch to 1.5 inches high. And it's really beautiful, because it shrunk everything else down. You could see almost all the original features that you had in there. It's just that the pressure had squeezed it equally from all directions and had compressed all the air in the styrofoam out and had compressed it down to something very, very small. Okay, so our hydrostatic force our hydrostatic force then is going to equal to our pressure, and our pressure is going to equal to W, which is our weight density, times depth, and we're going to use H for depth here because we're going to be taking derivatives and use D for derivatives. So H is our depth. So hydrostatic force is going to be equal to pressure times the area. So more force means more area, or a bigger area means you're going to have more force. The hydrostatic pressure would be the same, but if you've got more area, then you're exerting more force on it. So ultimately, this comes down to finding W times your depth times your area. All right, so let's take a look then. Now, before I do that, now, for horizontal surfaces, the pressure is the same everywhere because the depth doesn't change. So your fluid force is going to equal to your weight density times H times the area over which it is acting. Okay? Now for vertical plates, or for vertical surfaces, we need to use calculus. One example I saw of this was when they installed a dolphin tank at the Texas State Aquarium when I was living and working in Corpus Christi. And they came in and they were putting a big window, plexiglass window, right in the middle of all this so people could look back in. And obviously what they were interested in was the force that was being exerted across this, the total force that's going to be exerted across this piece of glass. If you didn't calculate it right, it was going to break. And a lot of people were going to get wet, and there were going to be some very unhappy dolphins if you had them flopping around on the floor. Now, when you deal with vertical surfaces, very important, always look for symmetries. Now we're going to be dealing also with things where our density, our weight density, is going to be constant. You see problems like, for instance, in the ocean where the weight of seawater does change with temperature, and as temperature changes, then this will change. But for our problems, our weight density is going to be a constant. And for fresh water, it tends to be 62.4 pounds per cubic foot. Or 9,800 newtons per meter cubed, which is just converting the acceleration of gravity out. Okay, so before I work through some examples, let's write some steps out. And bear with me, because as we work through an example, I think you'll see this. So your steps, number one, again, this is very important. Draw a picture. It may look very simple, very straightforward. Draw a picture and make sure it is. Make sure there's some complexity you don't come up with. Then you need to set up a coordinate system because one is usually not given to you. That takes advantage of symmetries. So if you remember with the dolphin tank window, they had a rectangular window. In this case, they also had some non-rectangular, and those added into it. And so what they did was, the coordinate system they set up was, here we had the origin right here. And so essentially all they did was just find this, the force on this part, and then the force on this part, or they took this half of it. They found that force and multiplied it by 2 to get them to this guy right here. Okay, so set up a coordinate system that takes advantage of symmetries, so you can do an easier problem, especially one where you got 0 on part of your bounds that you're integrating to make your arithmetic a lot easier. Okay, the third thing you need to do is take a horizontal, and I do mean horizontal here. You want to make sure it's perpendicular to your depth. In other words, essentially what I'm doing is I'm going to take a very thin horizontal slice through this thing. And remember, we talked about that our force then, our total force, is only dependent on the area that we've got and the depth. So we're going to take a very thin horizontal slice where our depth becomes, or the change in depth approaches 0. So we're going to take a horizontal slice. The fourth thing you're going to do is find a general equation for the, it should be an F, for the length of the slice. All right, in other words, here to here is going to be my L. All right, and in this case, the way we have it set up, actually, then my L from here to here is going to be X. So my L is going to be 2X. And I notice that it does not change as I go up and down. So in this case, once I've got X, I know what my width is. It's going to be the same. It will be constant. So now you got that, your area is going to be L times, and you need this, if it's not constant, you need to solve it so you have an X equals, so you have L of Y times dy, where dy is the height of this very small slice that we're taking. And again, you should notice that conceptually this is very similar to what we've already been doing. Number 5, then you need to find another equation. You need to find a general equation for the depth of all slices. Again, going back to the dolphin tank, we had and the top of the water was right here. So essentially the depth, if I used this as my 0, then would be my height of my window, my Y, and we know that we knew what the distance here was. So it would be basically my total height here, if I remember right, was about 12 feet. So my height of my window would be 12 minus y, and that would give me where my slice is. It's 12 minus the height of whatever that is. All right, now, at this point, believe it or not, you've done most of the hard work. Now you need to find your depth ranges. And we arbitrarily set this to be 0, and then since this was 12 feet, we knew this was 3 feet. Our depth range in this case was 0 to 9 feet. Okay, now we're ready to actually, believe it or not, do some calculus. So my force now is going to be equal to my weight density, and we're going to assume that that's a constant for the problems you do. If not, you can't pull it out. Times the integral of my depth ranges of my depth. All right, and W times this gives me pressure, times my area, which is my length of y, times dy. And this is my area. And then when you integrate across the whole thing, you end up with your answer. So let's work a couple of examples here. The first one is we want to find the force on a trapezoidal wall of a tank. And the picture that they give you looks like this, where the top of the trapezoid was 4 feet across, the bottom was 2, and the height was 3. So there's my step 1. So step 2 now, I'm going to set up my coordinate system. And what I want to do is I'm going to bring this thing straight down the middle, because I notice I have symmetry on either side here. So my coordinate system then is going to look like this, and I'm going to have my 0 at the bottom of it. So here's my origin, 0, 0. And I'm going to draw my tank in, so I have to go over 1 here, 1 here. Then I go up 1, 2, 3. See, now I've got a coordinate system. And then I go over 1 more. So here's 1 end, this is -2, here's 2, and there we go. And now I can come in and I know that the coordinate of this point is 2, 3. Coordinate of this point is -2, 3, because we're symmetrical across the y-axis. This is -1, 0, and this point here was going to be 1, 0. And you notice I got a straight line here. All right, so that's step 2. Then step 3, I'm going to take my slice right through there. There's my slice. All right. And my slice is going to be at some unspecified distance up, which we're going to call y. So what I need to do now is we're going to assume that this thing's full. Find the force on the tank. Well, obviously you need the force on the tank to make sure it doesn't break. So my depth for this slice then was going to equal to 3 minus y, since this is 3. Okay, so we've got that. Now we need to find an x. And you notice, length. And so what I'm going to do now is I'm just going to split this thing down the middle. So my length is going to equal to x. but we want length as a function of y. So what we need to do then is find an equation for this thing right there. And that's usually pretty typical. To convert your x length into y, you need to solve this. And so what we need to find this. So y is going to equal to, we've got a line mx plus b. My slope, excuse me, is going to equal to let's see, y2 minus y1, so it's going to be 3 minus 0 over 2 minus 1, which is 3. So now I'm going to have y, and I'm going to pick this point because it will be y minus 0. Then it will be equal to 3 times x minus 1, or y equals to 3x minus 3. And then I need to solve this for x, because I want an x equals. So 3x is going to equal to y plus 3, or x equals to y plus 3 over 3. And so now my L of y, notice this is just a function of y, is going to be y plus 3 over 3. And that's how I get this length here in terms of my depth, or the height up from my coordinate system. That's my L of y. So now that we've got that, we've done the hard part. Now we can come in and do the easy part, which, believe it or not, is the calculus. So my force then, oh, and this is fresh water. So my W, my weight density is going to be 62.4. We'll deal with pounds. 62.4 pounds per cubic foot. So my force now, and now remember, I only found for half of that, so I'm going to need to multiply by 2. And I'm going to have my integral. Now, what's the depth of this thing? It's going to range from 0 to 3. So it's going to be 0 to 3 of my 3 minus y, which was my h of y, times my y plus 3 over 3, which is my L of y dy. Okay, now this looks like a pain, except I multiplied by 1/3. So I'm going to go ahead and bring that out. So F then is going to equal to, it's 124.8 over 3 times the integral from 0 to 3 of 3 minus y times y plus 3 dy. And when you expand this out, this was 41.6 out front, times the integral. When you expand everything out, you end up with 9 minus y squared, because I've got a plus 3y and a minus 3y. So you end up total with a 9 minus y squared dy. And now we integrate that thing. So that gives me force is going to equal 41.6 times 9y, again evaluated from 0 to 3, which is going to be nice because the 0 term will drop out on us, minus 1/3 y cubed, evaluated from 0 to 3. Or force is 41.6 times 9 times 3. But always write it out. 9 times 3 minus 0, which is evaluating this thing, minus 1/3 of 3 cubed, which is 27 minus 0. or my force is 41.6 times 27, no wait. Yeah, 27 minus 9, and it worked out to be about 748.8 pounds is the total force acting on the side of that tank wall. Okay, one more example. And here I'm dealing with a triangular vertical plate. In my picture, this thing's submerged, where the top of it is down 3 feet. It's 9 feet by 6 feet. And excuse me, 9 meters, 6 meters, we're 3 meters down. And we're dealing with fresh water, and since we're in metric, we're going to deal with our 9,800 newtons per cubic meter. All right, so now I'm going to come back in and set up my coordinate system. I'm going to set this thing up right through the middle here. So here's my coordinate system. Here's 0. I have 3, 6, 9, 12, 3, 6. And I know that this is my triangular plate right here. Okay, slice I'm going to take right through here. And so my depth, well, that's my unspecified y value up. So my depth function, and this is, remember where we're filled to, is going to be 12 minus y. All right, now we need to do our length function. And this gets a little bit more complicated, but you should recognize this as being very, very similar to what we had before. So my point here then is going to be 0, 9. And this point is 6, 0. And again, I've got a straight line. So I'm going to have slope is, now on some of these you'll be lucky when they're not straight lines, they will give you the equation. So my slope is going to be 9 minus 0 over 0 minus 6, which is a negative 3 halves. So I'm going to have y minus 0, I'm going to pick this point. It'll be negative 3 halves x minus 6, or y equals negative 3 halves x plus 9. I need to solve this. So I'm going to solve it for x. So I'm going to have y plus 9, excuse me, y minus 9. Is going to equal negative 3 halves x. And then I'll multiply by negative 2/3. So I'm going to end up with x equals negative 2/3 y plus 9, which is just multiplying 2/3 by, not 9. Six. It's a negative because I'm multiplying by two positives. So now what I've got then is this is my L of y that I've got, which gives me my length. So now we can come back in and get to the sexier part of all of this, which is actually do our integration. Now, I'm going to integrate this thing. Remember, I'm only interested in the depths over the plate. So my A is going to be 0, and my B is going to be 9. So I'm going to have my 9800, and I only have one triangle. Okay, you could, if you had another one out here like this, then you would have done 2 times it, times the integral from 0 to 9 of my h of y, which is 12 minus y, times my L of y, which is 6 minus 2/3 y, dy, or my force is going to be equal to 9800 times the integral from 0 to 9, and then I'm going to expand this out, and it worked out to be 2/3 y squared minus 14y plus 72 dy. And this is a nice integral, and I'm not going to do this. This is a nice little re-wop integral, and you notice you're going to end up with everything as a function of y in here. This term is 0. It makes it really nice. So spend a little bit of time coming back through and setting up what you got to do. So most work is going to be done in setting up coordinate system. So you can take advantage of symmetries and always try to set it up so one bounds of your integral is going to be 0. And this is, again, in drawing your picture and setting it up. Then oftentimes the other part, your h of y, your h of y is usually pretty easy. You look for your top and you subtract the general y value. Now the L of y can mean solving for x equals in the length of the plate or length of slice. And then after that, then the other thing is in doing the polynomial division. The easy part is the calculus. All right? So this is what you're going to have to do. Now, the only difference, and you won't actually have to do these, but if w is a function of y, then all you have to do then is bring it back inside, end up really having to do a lot more multiplication to do all this thing. But as far as the calculus, it really makes almost no difference with them at all. So if your w is constant, it's rather straightforward. If your w is not, again, it's just a matter of instead of multiplying outside, you bring it in, and it just gives you some additional polynomial multiplications that you have to do.